Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillah, and a very good day. So this is the last subtopic of the DC machine, which is a DC generator. So as mentioned before in our first class on the electrical machine, so the DC motor is also can be operated as a DC generator, and it is actually depends on the power flow, the energy flow. Okay, so right now for DC generator, meaning that the energy is converted from the mechanical into electrical energy. Okay, so as a definition, so generators convert kinetic energy from a prime mover. So this prime mover can be um, anything that can move the rotation of the rotor. It can be from the steam turbine or a diesel engine, okay, into an electrical energy. So, so several connections of the DC generator was illustrated in figure 16.29, which is I will show in this slide, okay. So, but for this syllabus, we only will discuss one DC generators only, which is the separately excited DC generator. Okay, so this is the several types of the DC generators. The first one is a separately excited DC generator. So as you can see here, we have the prime mover here, which is maybe the from the hydroelectric turbine or something that can move that can actually rotate the motor here, so rotate the machine here. So it will produce from this conversion, okay, electromagnetic conversion here, it will induce a voltage and also a current, okay, when you connect with a load here. And this is the V load here. And as you notice, we need also the field circuit. Okay, so field circuit is used to produce flux. Okay, because we know that IF is proportional with flux. Okay, why flux is used? Because if you notice the back EMF here, which is the voltage induced due to the rotation of this uh, rotor. Okay, so the back EMF, the value is depends on the K, which is a constant, multiply flux, okay, and multiply with the speed. So if there is no flux produced by this field circuit, so there will be no electrical, there will be no voltage induced. Okay, so that's why we this circuit is very important. Okay, and the second one is the shunt DC generator. So as you can see, um, because of the name, the field circuit is connected in parallel with the armature circuit. So this is your field circuit here, okay, where we have a variable resistance that you can adjust to control the value of the field current, okay, and we have the IA, and IA plus IF is actually equals to I load. Okay, and then the last one is the should be this one is the compound. Okay, not a series. This is a compound. Um, where as you can see, as mentioned before, compound is the where the circuit is the combination of series and also parallel. Okay. So, but we are only concentrating on this one, separately excited DC motor. So, separately excited DC generator. Okay, so the equivalent circuit for a separately excited DC motor or DC generator is shown in the figure, the previous figure. So, a prime mover, which is from the turbine and so on, the rotation, will drive the armature shaft, at the angular speed omega m. Okay, and the external DC source is supplied to the IF circuit to produce the field, produce the field or produce the flux actually. And then from that interaction, we will produce, we will induce armature voltage, which is right now is actually EA. Okay, and when you connect with a load, okay, so it will produce a current and also a voltage. Okay. So, but however, because of the armature resistance value, so the load voltage will actually reduce or decrease as the load current increase. Okay, this is happen when we assume that the speed is constant and the field current is also constant. So as shown here. So this is the graph of the voltage load versus the current load here. Okay, where this one is actually VL is equals to EA minus IARA. Okay, this is generator, right? So for motor is actually EA plus IARA. Okay, so this is for motor. But for generator, so we are using this one because the current right now is actually going back to the supply. So as you can see, if IA is increased, we will have a voltage of the load will actually reduce. Okay, so as mentioned here, so this is the value of IA, the value of the IL. So if IL is increased towards this value, you can see that the value of the voltage will actually reduce because of the voltage drop across the armature resistance. So this is the line for the separately excited DC generator. Okay, but for shunt connected, the voltage drop will become much larger because of the effect of the field weakening. So field weakening is actually where the IF is actually reduced. Okay, so when IF is reduced, the flux is also reduced, and this will make the field weaken. Okay, the magnetic field weaken. So why IF is reduced when IA is increased, when IL is increased? Because as you can see from this figure, okay, so this is your I load. Okay, to increase the I load, okay, while maintaining the IA, so IF must be reduced. Okay, so that's why when IL is increased, so IF must be reduced. So that's why we have the this one. Okay, so have a much more voltage drop compared to separately excited DC motor. So voltage regulation, okay, so some application, it is desirable for the load voltage to be nearly independent of load current. So a measure of the amount of decrease in load voltage with current is the percentage of load voltage regulation. So this is actually the same with the line, transmission line, the transformer and so on. So this is one of the parameters that will assess the performance of the generator. Okay, so if the voltage regulation is higher in terms of percentage, meaning that the voltage drop, the difference between no load and full load is very, very small. So it is desirable to have that the no load and full load values is almost the same. So meaning that if you have the difference, meaning that you have some kind of maybe high losses, okay, due to the internal resistance and so on. So what is the V no load? So V no load is actually is the voltage from the terminal when your load is actually zero or no load voltage. Okay, so for example, okay, so this one, the circuit. So right now, this is your V load and this is your voltage induced due to the rotation of the motor of the machine. Okay, so this is your RA. So when it is open circuit, so the voltage across this terminal is called V no load. And from here, you can see that IEE will be 0, right? Because there is no load connected. And then it is open circuit. So V no load is equal to the voltage induced, which is EA. Okay, and V full load is actually the voltage across when VL here when you connect with a full load, which is 100% of its rated value. Okay, so from here you will see that the voltage VL is equals to EA minus IA RA. Okay, so this is the advantage of a separately excited DC motor, where the load voltage can be adjusted over a wide range of varying by varying the field current, either by changing VF or by changing the R adjust. And also the load voltage is proportional to the speed. So performance calculations for separately excited DC generator. So as for DC motor, the following equation also can be applied in the DC generator. So we have already obtained this one. Okay, we know already this one, the voltage induced, which is the back EMF, and the torque developed by the machine here. And referring to the figure, so right now this one is EA is equal to RAIA plus VL, or sometimes also you can use this one, VL is equal to EA minus IA RA, is actually the same. Okay, and this is the armature circuit equation, and this is the for the field circuit equations. So these two circuits are also important, because without field circuit, okay, the motor, the armature circuit also cannot run, because because field circuit will produce flux. Okay, and the efficiency. So this is the general equation, P out over P in. Okay, and this is the power flow from the prime mover, which is from the mechanical side into a electrical side. So from the so the power input here is due to the mechanical energy, which is the torque input multiplied with the speed, okay, of the prime mover here. And then we have some losses, friction and windage losses, which is cannot be calculated, okay, based if you are in this class. And then we have also eddy current and also hysteresis current going on here. So, and then from that, after we subtract this one and this one, we will have the power developed by the generator here, which is you can calculate by using EA multiplied with IA. And this is actually equal to torque developed multiplied with the speed. So as you can see, the torque developed and torque input is different. Okay, this is actually torque developed is actually equal to T in minus T loss, or you can say that torque losses due to the friction and so on is equals to T developed T in minus T developed. Okay. And the power developed by the generator can be computed by using IEA multiplied with IA. And then of course, at the electrical part, we have losses due to the armature circuit, which is I square RA, and also field circuit. But this one is only when you consider a circuit which is a shunt DC motor and so on. For electrical, for the separately excited DC motor, this field circuit losses is not considered. Okay, so this is not considered for separately excited DC motor, DC generator. Okay, and lastly, the P out, which is after you subtract this one. So P out is actually equals to P developed minus armature losses, okay, for separately excited motor. For separate excited DC generator, P out is equal to P developed minus armature losses. So this is the example, one example that taken from the this book, Alan R. Hambley. So, and the solution will be discussed during our class. Okay, I think that's all. That conclude my presentation for this DC generator, and I think we finish on this topic, the DC motor, and sorry, DC machine. So for the next class, we will go for the AC machine. Okay, thank you very much.